Welcome you all. In this session, you are going to discuss about equal area criteria for stability analysis. Outcome: after successful completion of the session, the student would able to analyze the stability of power system using equal area criteria. Equal area criteria. The stability of single machine connected to infinite bus can be studied by the use of equal area criteria. The method is used for quick prediction of stability. Thus, the method is based on graphical interpretation of energy stored in rotating mass as an aid to determine if the machine maintains its stability after a disturbance. This method is only applicable to one machine system connected to an infinite bus or a two machine system. This method provides a physical insignificant to the dynamic behavior of machine. This is a simple graphical method to predict the transient stability of two machine system or a single machine against infinite bus. The criteria does not require a swing equation or the solution of swing equation to determine the stability. That is the advantage. The stability conditions can be determined by equating the area of segments of power angle diagram. So with the help of power angle diagram, we can represent or we can identify whether the system is stable or not. So here the diagram shows this is the graphical representation of power angle curve. So this is the power angle curve which we say. So here the x-axis represents the del value in terms of radians and the y-axis is the power value in terms of per unit. So here you can see the curve. It is almost like a parabola. Like okay. Now from this with respect to this figure, a machine is operating, let us take this delta naught corresponding to mechanical power input. This input power is taken as pm naught and which is equal to pe naught at this point. Pm naught, this is pm and this is pe, so both are equal at this point. There is a sudden increase in mechanical power input. It is represented by the line, next line. Okay, if you are going for a next line, that is if increases, it goes on to the next line. So since Pm is greater than Pe, the acceleration takes place. So if increases, the acceleration takes place, and if decreases, the deceleration takes place. So this is how it is given. So the multiplying the swing equation by d del by dt on both sides. Here you can see what happens. H omega s d by dt of d del divided by dt the whole square, which is equal to pm minus pe into dl by dt. I am multiplying d del by dt on both sides. So now again I can, so just I am multiplying this inside, so I am getting that d by dt d del by dt the whole square is equal to 2 times d del by dt into d square del by dt square, multiplying both sides of the above equation by dt and then integrating between the arbitrary values of del theta and del c. So here the equation is like this. Once a fault occurs, the machine starts accelerating. Once a fault is cleared, then the machine keeps on accelerating before it reaches the peak value del C. Del C is the peak value. So now the area of acceleration is taken as A1, the first area. That is A1 is equal to integral del naught to del C, Pm minus Pe d del, which is equal to 0. The area of deceleration, the second area, A2 is equal to del C2 del E, the second maximum value. Pe minus Pm d del is equal to 0. And if the areas are equal, A1 is equal, then the system is said to be stable. Say the acceleration area as well as the deceleration area must be equal. If suppose if they are equal, then we can say that the system is said to be stable, or else it is unstable. This is how we find the stability of a system with this graphical representation or with the help of this power angle curve. This is what. Critical clearing angle. So del C, the maximum allowable value of clearance time of an angle system to remain stable is known as the critical clearing angle time. So the expression can be represented as integral. So as I told, it is for stable case a1 is equal to a2, that the both the area will be same, right? So a1 is equal to a2. At this case, what happens? I can equate both the areas. So integral del naught to del c pm minus pe d del is equal to del c to del pe minus pm del d. So substituting p is equal to 0 in swing equation. So p equal to 0 means d square del by dt square is equal to omega 2h into p. Integrating the above equation, I'll be getting d by, so while integrating it becomes d del by dt, which is equal to integral 0 to t omega by 2h pm dt, which is again equal to omega s divided by 2h into pmt. So replacing by del cr and t by tcr, the above equation, we get the critical clearing time. Tcr is equal to square root of 4h by omega pm into del cr minus del naught. This is the critical clearing time. Factors affecting transient stability. Strength of transient network with a system and tie lines to be adjacent system. The characteristics of generating units including inertia of rotating parts and electrical properties such as transient reactance and magnetic saturation characteristics of stator and rotor. Speed with which the fault lines or equipments can be disconnected. So these are the factors which affects this transient stability. Thank you.